Welcome back to Random Maths Inc. It's the penultimate episode of 12 classes. We're on the 11th class, and today we're going to be talking about a class which some of you might classify as a maths class. When I took it, it was more of a computer science class, and this class is called Optimisation. So let's get right into it. Now, what is optimization all about? Well, it's a bit hard to give a solid definition for optimization, but the idea of it is that, sometimes you want to do a certain action, you want to do something, but you can't really just do it in a way, right? Because there are constraints that stops you from, for example, maybe getting to maximum efficiency or something like that. There's constraints put on you, so sometimes you have to think about what is the best action that you can take given the circumstances given to you, right? So examples of things that you might be able to optimize. So for example, maybe the simplest example, suppose you own a shop, maybe you own a bakery or something, right? And in your bakery, just for simplicity, suppose you only sell two things. You either sell a cake, which I cannot draw, but I guess that's probably the closest one you can get to. You either sell a cake, a red cake for some reason, and bread, which I think that looks good enough. So you sell either cake and bread. What are those two, right? And in the morning when you wake up to your bakery, you have to make some cake and you have to make some bread, right? In order to sell it at your bakery. But you cannot make unlimited cake and you cannot make unlimited bread because, well, it turns out that next door to your bakery you have a stock house or somewhere where you store a lot of raw materials for the cake and the bread. Maybe you store flour, maybe you store like yeast. Do you need yeast in cake? I don't really know. Maybe you have some water. Of course you need water and everything. Things like that. So you have different raw materials inside your warehouse that you can make cake and you can make bread out of, but you don't have unlimited amounts of these material. There is a limited amount of flour, yeast, or water, or whatever other things that you have in order to make your cake and your bread. And so the question is, if you want to make the maximum amount of money that day, then how many cakes should you make and how many bread should you make, given that you have a limited amount of material, right? So maybe like the cake sells for 10 pounds and maybe the bread only sells for 3 pounds per loaf or something like that. So given these materials that you have, how many cakes should you make and how many bread should you make in order to maximize your profit, right? So you can see here, you have an objective, you have something that you want to do. You want to maximize your profit. That's what you want to do. But you can't just maximize your profit uncontrollably. You can't just make infinitely many cakes and infinitely many bread because you have constraints on your system, on your problem, right? And your constraints is the materials that you have. So this is sort of an optimization problem that you have to get the most profit out of this given the constraints that you have. There are also other problems out there as well in your optimization problems. So another example is maybe you are on a night out with your friends and you're about to go home, but all your friends are drunk except for you. And so you're here with a car, right? And in the car you have yourself and your other friends, which I won't draw because it will get way too small, right? And maybe you have 4 or 5 friends and they all live at 4 or 5 different places, right? Something like that. And then you also have your own house, which you have to get back to, right? So there's A, B, C, D, E, places or something like that. So the question is, who should you drop off first? Which friend should you send home first? Maybe one of the parties, maybe you can just go, for example, you can maybe go there and then you go there, maybe there, and there, then there, like that. Something like that. Maybe that's one path you can send your friends off. Maybe there's another path. But the question is, what's the most efficient path that you can take? That sort of thing. So that's what you want to do. You want to take the most efficient path. But then there's also other constraints as well that's maybe put on your system. So for example, you want to get to your house the last, right? Because you want to send all your friends off first and then get to your house. So that's maybe a constraint that you have to get to your house. The last place you visit is your house. maybe there's also other constraints. Maybe you can't have friend A and friend B be alone with you in the car for some weird reason. So maybe you have to send A off first or B off first or something like that. So there's other constraints that you might want to think about. So this is another example of an optimization problem as well. There's also other optimization problems or other problems that you can phrase as an optimization problem, which are maybe a bit more scientific. So if you think about a problem of having a graph. So if you have like a graph, you have some data points, something like that. Maybe, you're plotting some data and you want to find the best fit line, right? So you want to find which line sort of describes the point linearly in the best fashion. So this is sort of an optimization problem as well, because what you're trying to minimize is you're trying to minimize the distance between each of the points to the line, right? That distance, that sort of thing. So that, in a way, doing that is also an optimization problem. So you can see that optimization problem comes in many different forms and different shapes and different sizes. And it's really useful in daily lives because, well, there's loads of optimization problems out there, right? And so the idea behind optimization is, you have problems in real life. You have like these situations in real life. And the question you might want to ask is, how can you take the problems that you have and phrase it in a way that you can then, find out the optimal solution for? So as you can see in all of these problems, there are a couple of things which are similar. There's two key things which are similar in both of them, is that you have an objective and you have constraints, right? The objective is what you want to do. You want to maximize something. And the constraint sort of is something that stops you from, just going wild with it. It's sort of like, is like what you can do in order to maximize your thing, right? So in this case, maximize profit, constraints being the material. This case, maybe maximize, or minimize, in this case, minimize the distance traveled. And the constraint maybe is visit your house last. And this one maybe minimize these distances. And maybe there isn't a constraint, for example, right? Maybe in this case, the slope is positive. Maybe that could be a constraint, something like that. So these are examples of optimization problems. Now, as I've said, you take a problem that you have and you can phrase it as, as a mathematical problem. Because, if you just have a problem like this, you can't really solve them. It's really hard to solve them. So you have to find a way in order to take a problem like this and then phrase it in a way that you can understand. Or at least you can do something with it mathematically in order to find the optimal solution. And there's many, many different ways in order to do so. There's many sort of sub-problems. There are many problems in optimization which you can phrase it into. You can phrase a general problem into. So as an example, so suppose we can consider something called a linear program. A linear program is a general optimization problem. A linear program is a type of an optimization problem, right? So again, it will be more of a mathematical expression. An optimization problem in a term of a more in terms of a more mathematical notation. So in linear programs, first you have some things you can vary, right? So you have a list of variables, which in this case we'll just very lazily call it x1, x2, and so on to maybe xn, for example. Then you have, your objective, what you want to do, right? In this case, you want to maximize some expression c1 x1 plus c2 x2 plus so on. So just linear combination of these variables here, right? Of course, again, you need to have some constraints. So the constraints will be in the form of a11 x1 plus a12 x2 plus so on is less than v1. Some number where all A's, B's, and C's are just numbers. But maybe you have more than one constraint. So maybe you have another constraint, a21 x1 plus a22 x2 plus so on, again, less than v2, right? So you have a list of variables. These are the things that you can vary in order to get an optimal solution. You can vary all of these things in order to get the optimal solution. The optimal solution will have a maximum amount of whatever this computes out to, and there's a set of constraints that you have to follow. So you can't just change x to be anything. And usually also you can have maybe x1 is greater than 0, x2 is also greater than 0, and so on. So this is what we call a linear program. And a linear program is, you can see, a more specific type of optimization problem. So it's a very specific optimization problem where all the objectives and all the constraints are written as linear equations. You can also express this more compactly in terms of as linear algebra notation. So variable, you can instead replace it with vector x, and then the objective function can just simply be the dot product between two vectors, the variable vector and the constant vector, sometimes written in this notation. The constraints can be written as a matrix, like so, and also this constraint, right? So that is a linear program. And as you can see, it's a very specific type of optimization problem. So maybe if you can take, a problem like this and you can phrase it as a linear program. In other words, you can maybe, for example, let the variable x1 be number of cakes produced, x2 be number of bread produced, and then the objective is, the cost, the profit that you can make, and then the constraints, you can phrase the constraints of having limits on each of the material. You can phrase it in these terms, then you can have a linear program. Then you can turn the problem that you have into a linear program. And that is good because there are ways you can solve the linear program. And the algorithm is called the simplex method, which in the briefest of sense, it goes as follows. So maybe just as a generalization, suppose you only have two variables you want to optimize. Looking like that, you can draw out your constraints as sort of a feasible region. So for example, if you have a point on here, that will represent some amount of x1 and some amount of x2, right? But all across this board, you cannot simply have all the points in all of these positions because of the constraints that you have. And so you can draw out some feasible regions. And it turns out that your constraints are quite nice, and the constraints will usually just be straight lines, or if in multiple dimensions, will be a plane. These constraints will create some lines. These constraints down here, which is usually limit your thing to just be up here. And so you have a feasible region that might, for example, look like this. So that means all the x1s and x2 pairs which are in this region will fit within the constraints. If you have a point out here, for example, that means the x1 and x2 pair here will not fit in your constraints and cannot be a solution. And it turns out you can also prove, which I won't show here, that the objective function will be maximized at one of the corners, at one of the places where your lines or your planes intersect. And so the simplex method, all you have to do is just check these points there, right? It sounds really simple, and the algorithm actually is not too bad. It takes relatively quick to solve it as well. And it's nice, and that's one property about linear programs. Linear programs, it's a more strict form. It's a lot harder to take any general problem and make it into a linear program. Like this problem, you can't make it into a linear program, and neither can this one. But if you can take a problem and make it into a linear program, you can solve it relatively easily and relatively quickly, right? What about if you don't have a linear program? As I've mentioned, linear programs are more specific. What if you have a more general type of optimization problem? Well, then what can you do? So what does a general optimization problem look like? Well, again, you'll have some objectives, right? You'll have some variables first. So maybe you have some variables. Just for simplicity, let's suppose you only have one variable. Maybe you can have multiple variables, and then you can express it as a vector, for example. The objective can just be, in this case, suppose you just want to say you can maximize some function, right? Some function of x, right? This function will just give you a real number, and this function can look like anything. It doesn't just have to be a linear combination of the variables. Maybe it can look like, for example, it can be maybe cosine of x1 plus sine of x2 plus something crazy like that. It could even be maybe, I don't know, x1 to the power of x2 plus x3 cubed, something like that. It can look like anything, basically. That's the point I'm trying to say, right? But then there are also maybe constraints that you have to follow, right? Constraints that you have to follow. Maybe you could have to say that g of x must be greater than 0. Or maybe there's multiple of these terms and something like that, right? So how can you solve a more general optimization problems like this? Well, if I graph out this function, what it might look like is it might look like this, right? I'll just draw it in one dimension because I'm too lazy to extend it to a higher dimension, right? something like that. So if you look by eye, you could sort of see that the maximum should be around here, right? But the computer doesn't really know that right from the start. Maybe the computer can guess, right, maybe we start off there, right? What you can do is the computer can ask itself, if I want to maximize the function, then which points is probably going to get me closer to the maximum? Of course, this is not the maximum, but if I want to get closer to the maximum, how should I move, right? So the computer what it can do is it can draw a slope, draw a tangent line, something like that. And then you can see that the slope is sort of going up in that direction. So the point then will want to check something that's probably closer to this side, right? If it goes to this side, then it'll actually start to go up. It'll actually start to follow the curve upwards, right? So then it might check here. Then it goes here, checks the slope again, and you can see that the slope is getting steeper in that direction. So maybe it takes a bigger step forward there, right? Now it checks the slope again. Again, it's an even bigger slope, so maybe it takes an even bigger step, something like that. And then eventually it will keep taking steps until it reaches this point at the top. And then it checks the slope of the point at the top, and it says, right, you know what? The slope up here is already 0, right? Which means that, it doesn't, if I go this way, I'll get less. The value of the point will be less. If I go this way, the value of the point will also be less. So I'm probably already at a maximum. Something like that. So the idea is you walking towards the higher points, right? So it's sort of like you walking up the mountain, but in this case, it's the point walking up to the direction that will take it higher and higher up the mountain, something like that. And that is basically the idea of things like gradient descent. So you might have heard things like Newton's method, which is, I think, something really similar. Basically, like, this is the idea of gradient descent, where you're using gradients to work out which way you should sort of walk. That is the way that you can solve your objective. The only problem with this method is that it only allows you to solve it for the objective there, right? So far, I've ignored the constraints. I haven't really considered the constraints in at all. And there are ways that you can also incorporate the constraints. The way that you can do so is by remodifying your objective function. The way that you can do so, which I cannot remember off the top of my head because I don't have notes here, but the way you can do so is you can say that you want to maximize some function like this, and then you can add an extra term in. So the term, I believe, might be something like minus this, or something looking like that, right? So you want to subtract this, right? So as you can see, no, actually, I think it is more like plus that or something like that. But the idea is you add in a term at the back here, your constraint term at the back, so that if the constraint is not correct, in other words, if you have like that, something like that, then it penalizes your objective function. And when it penalizes your objective function, it sort of, doesn't maximize it anymore. It sort of minimizes it. And maybe you can add like a log function or an exponential function to make sure that the penalized function like decreases a lot faster, something like that. I won't really get into that. You can sort of look that up. But basically this is, a more general optimization problem where you're just dealing with any old functions, unlike in linear programs where you're dealing with a more specific case, right, where the functions all have to be linear functions or linear equations and things like that, right? And so in optimization, you have like this really large range of problems that you can study, right? So you have problems which are said to be a lot more specific, right? And you have problems which are said to be more general, right? Specific in the sense that, the forms that you have to get into the problem into is a lot more specific. So for example, things like linear programs, and more general problems are problems like this one, where it's just any old function. You make no assumptions about how the functions look like. So as I've mentioned, linear programs fall on more specific side. General side maybe just, for example, I don't know, non-convex functions or convex functions. I'm not sure what's the proper terminology for it. Something like that. There's also other problems that sort of lies in the middle here. So there's things like quadratic programs, which is also a matrix, but you also allow for like second powers. There's things like a second order cone program, which I can't remember what it looks like. There's things like SDPs. Names of things that you can look up if you're more curious about them. Basically, this problem is a lot more specific, and some of these are sort of will apply to more problems. It's a lot easier to take any general problem and maybe fit them into one of these sections. So like on this end of the spectrum, you know, it's very easy to take any problem and phrase it into one of these problems, but then it's a lot harder to do so for this side of the spectrum. But there is also a trade-off, right? Because if a problem is more specific, then the time that you can take to solve the problem, the optimization problem, tends to be quicker, faster, right? So if you have a more specific optimization problem, then you sort of maybe know how the objective definitely looks like and how the constraints will definitely look like. And so it's a lot quicker to solve problems which are more specific. But if you have a more general problem, then it's a lot slower. So things like gradient descent is a lot slower to solve compared to, for example, the simplex method in order to solve linear programs. But the simplex method can only solve linear programs, and gradient descent can solve, well, pretty much all of these different problems out here. You can use gradient descent and throw it at basically anything, right? Unlike simplex method, where it only works with linear programs. So you have this sort of graph, this sort of, I didn't even get to the point there, but you have this sort of trade-offs. There's algorithms which are more specific, ways to optimize problems which are more specific but a lot faster, but only applies to a small subset of problems in the world. And there's problems and there's algorithms which, you know, applies to pretty much all optimization problems that you have, but takes a lot longer to solve because it is a more general algorithm, things like that. And so basically, in optimization, you learn about all these different classes of problems, these different classes of optimization problems, and you sort of talk about how you might go about optimizing them, things like that. And you also try to apply it to real life. So you might take a problem from real life, some of these problems that you see here, and then you can ask, well, how can I optimize them? Something like that. Like, how can I go about phrasing these problems in terms of mathematical expressions and then go about solving them? Of course, I only mentioned 2 types of optimization problems, and as you can see, there's loads of other ones, and it's a lot of fun. It's still a lot of fun. There's also other like small details about how to deal with optimization problems. Like, for example, how do you deal with 2 objective functions which are maybe conflicting with each other? Or linear programs have got things called duality, which I won't really get into, but that's basically optimization problems. That's basically optimization class. It's a really fun class that I took, and I really enjoyed this class because of, well, the math is really interesting, and it's also really applicable to the real world. And I think that's the greatest thing about maths. When you can use it in real life, it's amazing. But anyways, yeah, that's it for my little video on optimization class. And yeah, I hope you enjoyed the penultimate episode of 12 classes. It's going to come to an end soon. I'm really sorry about that. But anyways, thank you very much for watching this episode of 12 classes, and I'll see you guys again for the final episode tomorrow, where I talk about a maths class, which I won't really tell you much about. It's just a really fun maths class.